Okay. You keep telling me the speaker's not working. Okay.
Testing, 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 testing. That works. Caitlin, you're on the golf team, right? Did you guys have tournaments over break or no? Still too cold? Too much snow? I think Bree Vilmont told me if you use these brightly colored golf balls, you can play in the snow, but it's not at all preferable.
I use yellow golf balls. Like the only one I'm
Oh, okay. Thank you. I guess they come in fluorescent colors too, so, okay. So against the snow, they just, yeah, given Bree's personality, it doesn't really, I have no idea, it doesn't surprise me at all that she uses something like that. Thank you. She's a little bit on the different side, shall we say. Okay. Jacob Bracken, can you hear me?
Yeah, I can hear you.
Okay, good. All right. I did not expect you here. Didn't you guys get in at this morning?
No.
No? Last night? Pretty long week though.
Huh?
Pretty long week.
Oh.
How many games? 1, 2, 3, 4, 5, 6, 7, 8, 12 games? Okay. And you guys did well from what I could gather. Yeah. Hey. Okay, let's see what the sound sounds like.
Despite having a bad reputation.
Okay, yeah, that works. Back, might want to turn that down a bit. All right, it's going to be a skeleton crew this morning, so both baseball and softball had a very long week, and travel to some places was delayed by inclement weather, and then other people are having car trouble, so that's kind of the way it goes. Hope you guys enjoyed your week off. I worked all week, so I got a lot done. It was nice to experience something yesterday, what do we call it, warmth? Something above freezing, which we're supposed to get all week. So I'm looking forward to the crocuses coming up from the ground and showing me their beautiful purple petals. And I'm looking to that, and then the tulips following them, and then the daffodils following them. And should be a nice, glorious spring full of color. All right, we are going to talk about cholesterol. Cholesterol metabolism is not simple. So this particular video here will give you the basics. We'll then try to fill in the gaps after we learn just the basics. So let's take a look at this video and then we'll go from there, right? Try and get the sound right here.
Despite having a bad reputation as a high risk factor for cardiovascular diseases, cholesterol is an essential component of all animal cells. It is an integral part of the cell membrane, providing membrane fluidity and participating in a number of cellular processes. Cholesterol also serves as a precursor for production of bile, steroid hormones, and vitamin D. While the body can obtain cholesterol from food, many cells synthesize their own endogenous cholesterol. Cellular production of cholesterol is under negative feedback control. Low levels of intracellular cholesterol induce its own production, while high cholesterol levels inhibit it. Cholesterol, together with other lipids, is transported in blood plasma within large particles known as lipoproteins. A lipoprotein is an assembly of lipids and proteins. Lipoproteins are classified based on their density. Because lipids are lighter than proteins, particles that contain more lipids are larger in size but have a lower density. Different types of lipoproteins have different sets of proteins on their surface. These proteins serve as address tags, determining the destination and hence function of each lipoprotein. For example, low-density lipoprotein, LDL, carries cholesterol from the liver to other tissues, while high-density lipoprotein, HDL, returns excess cholesterol to the liver. Major events in cholesterol metabolism include dietary cholesterol is absorbed in the intestine and carried via blood circulation to the liver. The liver packages cholesterol pools, a combination of endogenous and dietary, together with triglycerides, another type of lipid, into particles of very low density lipoprotein, VLDL. VLDL travels in the bloodstream to other organs. During circulation, muscle and adipose tissues extract triglycerides from VLDL, turning it into low density lipoprotein, LDL. Peripheral cells take up LDL by endocytosis using LDL receptors. Cholesterol is used in cell membrane and other functions. Excess cholesterol is exported from the cells and delivered to high-density lipoprotein, HDL, to be returned to the liver in a process called reverse cholesterol transport. The liver uses cholesterol to produce bile. Bile is secreted to the intestine, where it helps break down fat. Part of this bile is excreted in the stomach. The rest is recycled back to the liver. LDL has the highest cholesterol content and is the major carrier of cholesterol in the blood. High levels of LDL in the blood are associated with cholesterol plaque buildup and cardiovascular diseases, such as heart attacks and strokes. For this reason, LDL is known as bad cholesterol. On the other hand, HDL is called good cholesterol because it removes excess cholesterol from tissues and the bloodstream. Common drugs used to lower cholesterol include inhibitors of endogenous cholesterol production, inhibitors of intestinal cholesterol absorption, and inhibitors of bile reuptake.
All right, that's the straight skinny on cholesterol metabolism. If you make a salad in the DC, you take your oil, you take your vinegar, you put them together, say, in a test tube. I don't know why you'd have a test tube in the DC, but let's say you do. And you shake it really hard. what happens? And then you wait a little while and they separate. You shake it a little harder. What happens? Same thing, right? You shake it even harder. What happens? Same thing. They don't mix, do they? So fat and cholesterol are fundamentally immiscible. One does not dissolve in the other. The point of this little mental exercise is to show you if the body just takes cholesterol and dumps it into the bloodstream is mainly water, isn't it? What's going to happen to that cholesterol? It's going to fall out of solution. It's going to fall out of solution. It's going to make a fat embolus inside your bloodstream. It's going to clog your blood vessel and you're going to have an infarction. So dumping free cholesterol into the bloodstream, is that a good idea? It's okay, you can say no. No, fat. Dumping just free fatty acids, free fat into the bloodstream, is that a good idea? No. So how does your body transport these around the bloodstream to other tissues? It uses a vehicle. It uses a taxi, if you will. Now I have a very silly example for this, and it goes like this. Let's say Bree over here is an exceedingly dangerous person. Let's say we cannot let her walk to the field house because she has this terrible temper and she beats people up. Every person she sees, she beats them up. She's just very, very dangerous. So if she walks to the field house, she's going to leave a trail of carnage all the way to the field house. So what do? We wrestle her to the floor and tie her up and throw her in a taxi, have the taxi driver to the field house. No one gets hurt. The upholstery gets damaged in the taxi, but Bree gets there and nobody gets hurt. The taxi takes the dangerous Bree to the field house. The taxi are these lipoprotein particles that will transport cholesterol and fat throughout the body. So cholesterol is essential for your body. Not only is it a biosynthetic precursor for things like vitamin D and biosalts that are used to help dissolve fats, so that dietary fats, so that your lipases secreted by the pancreas can degrade them. And then every steroid hormone your body makes, the precursor for those steroid hormones, their biosynthesis, is cholesterol. Cell membranes of every cell in your body also use cholesterol to regulate their rigidity and their fluidity. This is a strategy used by animal cells that's not used by plant or bacterial cells. Plants and bacteria tend to regulate the ratio of saturated to unsaturated fatty acids in their phospholipids. Plants have sterol in their membranes, but very little. And they don't have cholesterol in their membranes. They have a steroid called sitosterol or other lipids like that. They don't have cholesterol in their membranes. Plants will make cholesterol as a precursor to making sitosterol or other plant-based lipids. But it's just an intermediate, and it's a short-term intermediate. We use a lot of cholesterol in our membranes. Red blood cells, their membranes by weight, some 28% of their membranes by weight are cholesterol. So animal cell membranes, particularly mammals, have a lot of cholesterol in them. So this is cholesterol. Now, do I show this to you to make you break out in a cold sweat and say, ooh, chemistry? No. What I want you to see is that some of those carbons are black, others are red. So these particular red carbons here, 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 so on and so forth. Every other carbon, essentially, is made from this particular carbon of acetate. So cholesterol is a polymer of acetate. You take acetates and you string them all together, and that's how you make cholesterol. Of course, they're not moving. They never move when he's on, it seems. So since acetate is made from the breakdown of sugar and the breakdown of fat and the breakdown of several amino acids, you're going to take that and you're going to hook it to a carrier called coenzyme A. You make this molecule called acetyl coenzyme A. You're going to hook 3 of those acetyl coenzyme A's together. And you're going to make this molecule called beta-hydroxy beta-methyl glutaryl coenzyme A, which is mercifully abbreviated HMG coenzyme A. HMG coenzyme A, the structure of it is shown up there. It's 3 acetates linked together. You're going to reduce it. And you'll make this molecule called mevalonate. The enzyme that reduces beta-methyl beta-glutaryl coenzyme A, HMG coenzyme A, is called HMG-CoA reductase. HMG-CoA reductase is the most heavily regulated enzyme in this pathway. In cells, that's your money step. After you complete that step, the pathway is committed to making cholesterol. Therefore, that step is the most heavily regulated step in this pathway. So you link them together, you make mevalonate, then you activate the mevalonate by sticking the pyrophosphate group on it. You hook the mevalоnates together and you redo the double bonds. You make this intermediate that's called isopentenyl pyrophosphate, and then you hook those activated isoprene groups together. You hook them together head to head, and then you make geranyl pyrophosphate. After a head-to-head linkage, you link those tail to tail. You then get farnesyl pyrophosphate, and then you take the double bonds in there, and you just flip a electronic switch, and the electrons go like that, and you cyclize it. You make this intermediate called squalene. That enzyme is called squalene synthase. And after your farnesyl, after you get to farnesyl, all these other steps occur in the endoplasmic reticulum. Squalene then undergoes a variety of chemical modifications, and that gives you eventually lanosterol, and then lanosterol 15 steps later gets converted to cholesterol. Farnesyl is also used to make coenzyme Q10 or ubiquinone. Ubiquinone is a carrier for electrons in the mitochondria. It's very important for energy production. Dolichol is a carrier for these trees of sugars that are attached to proteins to make glycoproteins. So this pathway is used to make more than just cholesterol. It's also used to make some other intermediates. Now, because HMG-CoA reductase is the most heavily regulated part of this pathway, shutting down that particular step of the pathway is the one that's going to have the most knock-on effects. Therefore, the most popular drugs that are used to lower cholesterol are this group of drugs called the statins. And they inhibit that step. They inhibit HMG-CoA reductase. HMG-CoA reductase. That's a step you need to remember, HMG-CoA reductase. HMG-CoA reductase makes mevalonate from HMG coenzyme A. And no, I don't require you to know that HMG means beta hydroxy beta methyl glutarate coenzyme A. Just HMG is fine. So if you are, for example, a plant and you make things like vitamin K or vitamin E or vitamin A, you make it from that pathway. This pathway right here, that's how you make it. Carotenoids. Those are the orange compounds you find in plants. So that orange color in carrots, carotenoids are made from that same pathway because they're made from these activated isoprene units, that isopentenyl pyrophosphate. Rubber. Rubber is a polymer of activated isoprene units. Rubber is made from intermediates that come from that pathway. Several different plant hormones also come from that pathway. Coenzyme Q10 or ubiquinone, plastoquinone, vitamin D, which is made from cholesterol. They all come from that particular pathway. So in plants, you have a branch point, essentially. Instead of making lanosterol, you're going to make either stigmasterol or sitosterol. If it grows on the ground, it doesn't contain cholesterol when you eat it. That's one of the first things about cholesterol. One of the first ways you control cholesterol is by changing diet. Increased intake of plant-based foods will decrease your dietary intake of cholesterol. So cholesterol is going to come from diet, and it's going to come from what your body makes. Diet, you can control. What your body makes, that's genetics. That you can't control. So you can only ask people to control what they can't control. What they can't control, they just have to live with or deal with using medication. Oh, fungi. Fungi also are not going to make cholesterol. Fungi are going to make ergosterol. Ergosterol. So fungi will use ergosterol to control the rigidity and fluidity of their membranes. Plants, as we said, use sterols, but very little. Bacteria don't have any sterols in their membrane at all, except for one particular group of bacteria that steal it from you. So they don't really count. Now, ergosterol synthesis is the target of a group of antifungal drugs called azoles. And you'll notice all these drugs, they end in azole. So ketocon azole, flucon azole, itracon azole, voricon azole, posicon azole, your mother-in-law con azole, those are all azoles. They're all antifungal drugs. they inhibit the synthesis of ergosterol in fungi. Ketoconazole also interferes with sterol synthesis in your adrenal glands. And there is a condition known as Cushing syndrome. Ever heard of Cushing syndrome, anyone? You make excessive amounts of glucocorticoids in the adrenal cortex. You can also get Cushing syndrome by taking exogenous steroids like prednisone or drugs like that that mimic glucocorticoids. Excessive glucocorticoids will give you the effects of Cushing syndrome. Ketoconazole is actually also used to treat Cushing syndrome because it's an inhibitor of internal glucocorticoid production. So here are some of the members of this group of azoles. Miconazole is a drug that does not play well inside your body because the second you take it, it's subject to a very, very powerful first pass effect. So not enough of it gets to the area where you want to kill the fungi, but miconazole is used topically. And it's used in a lot of antifungal foot sprays. So athlete's foot fungal sprays, miconazole is found in a lot of those. That drug at the top there, amphotericin B. Amphotericin B is used for systemic fungal infections. That drug binds to ergosterol and forms a pore in the membrane. So now the membrane becomes leaky and the fungal cell dies. Amphotericin B, unfortunately, is not completely selective for ergosterol. Therefore, that drug has some toxicities because it will also bind to cholesterol and cause your cells to leak. It's used usually for fungal infections of the central nervous system, meningitis, and it's usually given intrathecally. And it's given when someone is at risk of dying. That's usually when you use it. All right, let's talk about what happens to cholesterol once it comes in to the body. The liver is going to be the main way station for cholesterol metabolism. Some of the cholesterol the liver collects will be used by the liver for its own cells. That will be a relatively small fraction of the cholesterol that comes to the liver. Your GI tract is drained by veins that go straight to the liver. So all of your dietary cholesterol will usually end up in the liver. That's not the first place it will go, as we will see, but it will eventually go to the liver and will get processed by the liver. A portion of cholesterol will be converted into bile salts. That cholesterol becomes known as biliary cholesterol. Biliary cholesterol. The rest will be transported. To be transported, it needs to be put in that vehicle we talked about. To be loaded into the vehicle, it needs to be converted into a cholesterol ester. A cholesterol ester. And the enzyme that converts cholesterol into a cholesterol ester is called acyl coenzyme A cholesterol acyl transferase. We're going to call that enzyme ACAT because ACAT's easier to remember than acyl coenzyme A cholesterol acyl transferase. We're just going to call it ACAT. ACAT will attach a fatty acid to the alcohol group of the cholesterol. So there's the alcohol up there. You attach a fatty acid to it. Now you've made a cholesterol ester. The cholesterol ester will then get loaded into a lipoprotein particle. So all your cholesterol that gets loaded into lipoprotein particles will be converted into a cholesterol ester unless it's free cholesterol that ends up in the membrane of the particle. So all tissues require cholesterol. To get the cholesterol to them, you transport it in these particles. And these particles are lipoprotein particles. You have to use these particles because fats and cholesterols are insoluble. This mode of transport gets past the solubility problem. All right. Okay, so you have in your notes, you have on page 70 a list of the different types of lipoprotein particles and their physical properties. Now, as you look at these different particles, they have different physical properties in that they have different densities. Those densities have to do with their level of cholesterol and fat and the ratio of cholesterol to fat. Chylomicrons are the least dense. They have a lot of fat relative to cholesterol. If we go below that, we see that there is very low density and then low density lipoprotein particles. Low density lipoprotein particles have a lot of cholesterol and very little fat. So we can see as your amount of fat that you have goes down, your density goes up because the cholesterol now will pack together. And these are cholesterol esters, by the way. They will pack together and they will become a more dense particle. So all of your lipoprotein particles have this particular structure. So on the outside, they have a phospholipid monolayer. Phospholipid monolayer. Your membranes are phospholipid bilayers. These are phospholipid monolayers. Embedded in the monolayer are, first of all, free cholesterol. So this is cholesterol that is unesterified. Also embedded are these proteins called apolipoproteins. Apolipoproteins, structurally speaking, are fascinating proteins. So the bottom part of them, if you can see, is pointed towards the cholesterol esters and the fat. So the bottom part of them really, really, really love fat, and they don't like water at all. The top of the protein faces the aqueous solution. It's very, very water loving. So these proteins are completely two-toned. The top side loves water. The bottom side hates water. And that's why they're able to sit in that monolayer towards the very, very hydrophobic internal part of the particle, lipoprotein particle, and be quite stable. When we get to the inside of the lipoprotein particle, we see esterified cholesterol. That's the thing that looks like a sausage that's kind of been squeezed and something's kind of bleeding out there. That's an esterified cholesterol. And then the things that look like E's, those are supposed to be fats. triglycerides. So you have 3 fatty acids esterified to a glycerol. And that's the little E's there. Notice you have lots of E's and lots of those cholesterol esters. So lipoprotein particles contain 1, fats, 2, cholesterol esters. The different lipoprotein particles have different ratios of fats to cholesterol esters. They also structurally have a phospholipid monolayer with free cholesterol embedded in the membrane plus apolipoproteins. All right, you with me so far? Good. Kennedy? Good? Yeah? Good. Bree? I don't worry about Bree. Yeah, I don't worry about you either. Cora? Good? Yeah? All right. Now, I really liked the part of that video where it called the apolipoproteins addresses. That's a nice way to think about apolipoproteins. So if we take a look at your table at the bottom of page 70, you'll notice that the apolipoproteins that are found in each of these different lipoprotein particles differs. So that's one of the ways you identify these particles is the particular apolipoproteins they have embedded in the phospholipid monolayer on the outside. Second thing you'll notice, take a look at the percentage of mass of, say, a chylomicron. Take a look at how much cholesterol they have. I'm on page 70, Bree, since you're flipping through this. Take a look at that. 2% cholesterol, 3% cholesterol esters, 90% triglycerol. Chylomicrons are mainly fat, aren't they? Now let's take a look at VLDL. What do you see? 4% cholesterol, 16% cholesterol esters, 60% triglycerols. They have a lot more cholesterol in them, don't they? Now let's look at LDL, below the IDL. 8% cholesterol, 42% by weight cholesterol esters, 7% triglycerols or fats. For triglycerol, just think fat. In fact, if you want to write above that fat, that may help you think about that. Triglycerol is just a biochemical term for a fat. LDL is mainly cholesterol, isn't it? So if it'll help you, you might want to write in the little margin, LDL, mainly cholesterol. Whereas at chylomicron, you might want to write next to that one, mainly fat. And the VLDL and the IDLs are somewhere in between. Take a look at the bottom now at the HDL. What do you see with the HDL? Or the HDL, what are they mainly? They're mainly protein, aren't they? The big numbers for those are in the protein. Yeah, they have a good deal of cholesterol. They have a good deal of cholesterol because they're cholesterol vacuums. But by weight, they're mainly protein. But whether they're HDL, LDL, VLDL, whatever, EIEIO, whatever, they have that structure. All lipoprotein particles have that structure. And let's rehearse again what that structure consists of. On the outside, they have a phospholipid monolayer. Embedded in the phospholipid monolayer are, just look at the picture. No, those are inside. Those are inside. Triglycerides are not in membrane. They're inside. Free, say it. Free cholesterol. Free cholesterol. And Bree, what else they have embedded in the monolayer? Just say proteins. Yeah, proteins. There's specific proteins for that. Okay, and then on the inside, they have triglycerides. Another term for triglycerides is fat. Thank you. I'm good at that. And what else? Cholesterol esters. Very good. Very good. And the different particles have different ratios of what to what? Cholesterol esters to fat. Very good. Very good. And they also have different arrays of apolipoproteins on the outside. And those apolipoproteins are kind of listed in the table on page 70. And then the pages before give you an idea of those different apolipoproteins and what they do. And blah, 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 so on and so forth. So take a look at page 68, 69, and that'll help you get an idea, because we're going to talk about some of these apolipoproteins and what they do. All right, moving on. So they're large macromolecular complexes. Most of them are made by the liver, not all of them though. And they have these specific proteins on the outside, apolipoproteins. Those apolipoproteins are abbreviated APO. And if you wanted on a test to call them APOs, I'd be fine with that, because I would know what you mean. And then they have the phospholipid monolayers with the cholesterol esters, triglycerides, free cholesterol, so on and so forth. All right. So here are 4 of the various particles that we'll talk about. Chylomicrons, and then you see pictures of them. And those are transmission electron microscope pictures of them. All of these have a different look, but they all have that structure. If you take that structure, shrink it down, you get essentially these different particles there. Chylomicrons, VLDLs, LDL, HDL, and you'll notice from page 70, page 70 on the lower table, it gives you the diameter of these. You'll notice as they get denser, they get smaller. That's another rule as well about these particles. They get denser, they get smaller. All right, let's start with the chylomicron. The chylomicron is made by the cells of the small intestine. It's made by the small cells of the small intestine. The intestinal enterocytes take up fat and they take up cholesterol, and they use it to assemble a chylomicron. After they make the chylomicron, they then secrete it, but it doesn't go into the bloodstream because it's too big to go into the bloodstream. It goes into the lymph. Now, from A&P, you might remember that your villi have within them a single lymphatic vessel called a lacteal. You also have several blood vessels, but again, the chylomicron, it's big, and it's too big to get into the bloodstream, so it goes into the lymph. Now we'll see why it does this in just a bit. So the chylomicron contains mostly fat, some cholesterol ester, and it'll have also in the monolayer some free cholesterol as well. And it has a few apolipoproteins. So it has apolipoproteins A, 1, 2, and 4. A, 1, 2, and 4. And then it also has another apolipoprotein that's specific to chylomicrons called ApoB, B as in baseball, 48. ApoB 48. The chylomicron will sojourn through the lymphatic system. Lymphatics are found throughout your body. They handle a lot of extracellular fluid from many tissues. One of those tissues are the muscles. Tell me something. What do resting muscles use as their primary energy source? Come on, HES majors. This is your bread and butter, muscles. Aerobically exercising muscles, anaerobic exercising muscles they use up muscle glycogen and they burn. Glycogen is degraded to, glycogen is a polymer of, you put it on your cereal in the morning, make it sweet. Thank you, glucose. Resting muscle uses free fatty acids. You ever heard the statement, the more muscle you have, the more fat you burn? It's actually true. Because resting muscle uses fatty acids. That spares the glucose for the brain, because the brain has a relatively absolute requirement for glucose. So the lymphatic vessels have on their surfaces an enzyme called lipoprotein lipase. And lipoprotein lipase is going to interact with the chylomicron and the VLDL particle in a very specific way. While the chylomicron circulates through the bloodstream, it'll interact with other particles. It will pick up another apolipoprotein particle, an apolipoprotein from these other particles, and the one it picks up is ApoC2. ApoC2. ApoC2 is an activator of lipoprotein lipase. Lipoprotein lipase is going to bind to the chylomicron, and it's going to degrade the fat inside the chylomicron. As it degrades the fat, the chylomicron will leak free fatty acids, and the tissue will take it up and use it as an energy source. So CM stands for chylomicron. It'll do the same thing to the VLDL. So as this particle sojourns through the lymph, it's being depleted of fat. It's being depleted of fat. And now that fat will get taken up, the fatty acids rather, will be taken up by these epithelial cells or muscle cells or whatever, and they will utilize it for their metabolic needs. So the activator of lipoprotein lipase, which is abbreviated LPL here, is ApoC2. It acquires ApoC2 throughout the bloodstream. This will cause the chylomicron to shrink. and the chylomicron will eventually go from the lymph to the blood. Where does the lymph essentially drain into the bloodstream? Was 263 that long ago? What's it called? Thoracic duct. The thoracic duct dumps the lymphatics into the venous blood, going back to the heart. The chylomicron remnant will then go to the liver, and it'll be taken up by the liver. There is a protein on the surface of the chylomicron called ApoE. The uptake, the ApoE mediated uptake of the chylomicron remnant by the liver is very fast. And now the liver has that cholesterol it needs to deal with. It will use that cholesterol to synthesize with the triglycerides a very low density lipoprotein particle. It will convert free cholesterol to cholesterol esters to do this. But if it has cholesterol esters, it will just use those as is to make the VLDL. It'll take fat, it'll take cholesterol esters, it'll synthesize a VLDL. And the VLDL, you can see, has more cholesterol than does the chylomicron. This is how your body is going to get cholesterol to the other tissues of the body. This is how it will deliver fat to adipocytes for storage. This is how it'll deliver fats to tissues that use fatty acids for their primary carbon and energy source. So what increases the synthesis of VLDLs? A fat-laden meal, of course, will increase synthesis of VLDLs, of course. Can you make fatty acids from sugar? Sure you can. How do we know? If you eat too much sugar, you get fatter, don't you? So you can make fat from sugar. You cannot make sugar from fat, though. Plants can do that. We can't. So high carbohydrate diets will also jack up your VLDLs as well. And the VLDL will contain fats, cholesterol, cholesterol esters, and then it will contain this array of apolipoproteins. Notice, instead of ApoB48, which is specific to chylomicrons, it has ApoB100. That ApoB100 is going to be really important in the next few slides. They are released straight into the bloodstream, and they'll transport fat to muscles and adipose tissue. Other tissues will be able to deplete the VLDL of fat by virtue of lipoprotein lipase. You'll deplete the VLDL of fat, you'll make a VLDL remnant, which can then be removed by the bloodstream because they still have ApoE. The uptake of VLDL remnants, that's ApoE mediated, is very fast. So here is blood plasma after a fast. See how nice and clear that is? If you were to take some text, put it behind that, you'd be able to read it. Here's your blood plasma right after a fat-rich meal. Think you could see through that? That is essentially what happens after a fat-rich meal. Your body releases quite a bit of VLDL. So your body is pretty efficient at this. Now, you may look at that and you may go, oh my word, gross, that happens to me? Yeah, that happens to you. And that gets delivered all over your body. So let's say Caitlin over here plays 18 holes of golf. So she walks 18 holes of golf, and then she sits down for a nice meal at the clubhouse. Her muscles now are screaming for repair because she's been walking, she's been hitting. There's that pressure that's put on the hip and the back, on the shoulders and what have you with that golf swing when you're using that driver or when you're trying to get out of the sand. Oh, you never hit in the sand trap, do you? Of course not, no. And the hand-eye that it takes to be good on the green and what have you, and so on and so forth, and then to stay out of the water and what have you. Those are all things that her muscles now need repair. That muscle, now that she's sitting down to a nice meal, she's resting, will be repaired by the fatty acids that come from that nice chicken dinner you had at the clubhouse. Now, I put this in here because many of you will deal with people who like to participate in fad diets. Many of these very low-fat diets that you see advertised tend to replace fats with cholesterol. Sorry, fats with carbohydrates. Carbohydrates will do just as good a job at jacking up your VLDL as will fats. In fact, high carbohydrate diets can increase your VLDL output faster than a high fat diet can. High fat diets will kind of do this, whereas high carbohydrate diets will kind of do this. So if you want to decrease VLDL output, you need to decrease the number of the calories you take in. Replacing one type of calorie with another doesn't really change the VLDL output. You want to decrease the number of calories. Likewise, for years, and why it won't die 1,000 deaths, I don't know, but the Atkins diet, where you essentially get rid of all carbohydrates and now just eat protein-laden diets and fat-laden diets. You eat a lot of meat and things like that, but you don't eat bread and potatoes. That will actually jack up your LDL really effectively. Also, because you're eating mainly meat, the amount of oxalate that you're going to actually take in will increase as well, and that can increase your risk for kidney stones. So try to dissuade people from fad diets, because fad diets really end up just not really working in general. There's no secret to losing weight except increasing your caloric expenditure and decreasing your caloric intake. I wish there was a miracle that I could prescribe to you for weight loss, but that's all the research pretty much says that's how you do it. Now, VLDL can be removed by the circulation by something called scavenger receptors. Scavenger receptors. And one of these is a so-called beta VLDL receptor. And these are used by cells of the kidney, cells of the adrenal gland, and then also some wandering cells can also remove that VLDL from circulation because they need cholesterol. So they can just grab VLDL and take it up using scavenger receptors as well. The upshot of all this is that VLDL is relatively easy to remove from circulation. Now, that VLDL goes through your body and it sojourns through your body. If you have a lot of muscles to repair, then that VLDL may be used up quite a bit. If you don't have as much muscle to repair and your caloric intake exceeds your caloric output and the needs, metabolic needs of your body, that VLDL now is going to sojourn through the body longer. And it's going to start to lose apolipoproteins, and it will start to lose fat. So now it'll be higher in cholesterol, and it will have lost a lot of the other apolipoproteins. So if it loses ApoC, so now it just has ApoE and ApoB100. It now becomes known as an intermediate density lipoprotein particle, or an IDL. IDLs can still be removed from circulation by the liver relatively easily. That's usually not a problem. If it loses ApoE, then the IDL now becomes known as an LDL. Why is losing ApoE such a big deal? Remember, the uptake of those particles by the liver, if it's ApoE mediated, it's very fast and it's largely unregulated. Once you lose ApoE, the only way the liver can remove you from circulation is by using ApoB100. Liver-based uptake via ApoB100 is highly regulated, and it's relatively slow. So removal of LDL from the body tends to be slow. That's why the residence time of an LDL particle in your bloodstream can vary from a few hours to 2.5 days. So the receptor that binds ApoB100 is called the LDL receptor. There's been a lot of work done on the LDL receptor. Turns out that there are different alleles, different forms, variations of that gene. Some of these receptors bind ApoB100 very tightly, very well, and remove that particle very quickly. Others just do it slightly well. So some people will remove LDL from their circulation pretty quickly. Others won't remove it so quickly. That's due to genetics. That's something you can't control. Now, this particular process is called receptor-mediated endocytosis. Receptor-mediated endocytosis. Once you remove the receptor from the cell surface, it needs to be recycled back to the surface. So as you take up more LDL, your capacity to take up LDL decreases because you have fewer receptors on your cell surface. Furthermore, as the amount of cholesterol in the cytosol increases, it decreases endogenous cholesterol synthesis. As it decreases cholesterol synthesis, one of the genes it will downregulate is the LDL receptor. So as you take up more cholesterol, your ability to take up more cholesterol decreases. that means the extra LDL you have out there, it's going to stay out there, and it's going to stay out there for a while. And if it stays out there for a while, it can work its way underneath endothelial cells that line blood vessels and become oxidized. And if it becomes oxidized, it's now going to help form plaques. That's what we'll get to on Wednesday. We'll talk about how the LDL particle forms atherosclerotic plaques and why it's known as bad cholesterol, a term that I just detest. Because it sounds like you're scolding cholesterol. Bad cholesterol, you naughty cholesterol. Yeah, whatever. But that's where it gets the term. All right, we'll pick this up on Wednesday. Again, I don't make any excuses that this is simple. It's not. This is multi-step. This is complicated, so just hang in there with me, okay?